Everyone, is the sound well? Is it okay like this? Great. My name is Boris, and as Victoria has already mentioned, I'm working right now in a technology company here based in Munich. My role is not only front-end developer, but also a researcher. So we do a lot of research in our daily work, and recently I've discovered a rather interesting topic that has been around for a good last decade, and I would like to share the thing with you. I would like to tell you what is quantum computing and why should we care about it. So first, let's start with classical computers. These are the devices that everyone in this room has. They are on our desks, in our pockets, or maybe even under our desks. These old-fashioned desktops, if you are in for retro stuff. But that's not interesting. We all know them, but what is interesting is this guy. That's a quantum computer. Really small thing. It's a circuit about a palm, a size of a palm, but what's happening inside is some very complicated physics stuff that I'll explain in a moment. First, let's start with a mental experiment. This is a coin from a country, it's called kopika, and as any coin, it has two sides. An obverse and a reverse. On the obverse, you see a number, on the reverse, you see a picture. And now let's imagine for a moment that somebody wanted to make a counterfeit coin, and he isn't really that good in counterfeiting and making fake things, so he has built a coin that has two sides that are the same. So you have 1 and 1 from both sides. And our task is to make sure if the coin is genuine or counterfeit. In normal classical computers, we would need two steps to do that. First, we compare this side, then we look at this side and we compare them. If they are the same, then the coin is counterfeit. If they are not, then the coin is genuine. The cool thing is, with quantum computer, you could do that with only one step. First, let's start with classical computers. The funny thing that you see over here is called a transistor. That's the most simple electronic unit, probably, and the only thing it does, it stores voltage. If there is a voltage, then your computer will interpret that as 1. If there is no voltage, then your computer will interpret that as 0. In processors of modern computers, there are thousands and billions of such things. Of course, they are way smaller, and computer uses them to perform all kinds of computations. And exactly from these transistors comes the binary language of your computer. So it doesn't matter if you have an application installed or you have your favorite movie. For a computer, it's all a series of zeros and ones. And since the beginning of classical computer age, one of Intel co-founders, namely Gordon Moore, whose photo you see on the slide, has stated an empirical law that says that the amount of transistors you have in your system will double approximately every 2 years. He wasn't that wrong, because nowadays we have processors that have 10 billions of transistors in them. And if you imagine that 40 years ago, in year 1971, we had a processor that had only 2,300 transistors, you can imagine the fast development the computer industry has made. Why is that? Why do we need more transistors? The thing is, with classical computations, to get better performance, you need more transistors, more or less, if you approximate. And there are really complicated problems modern computers are solving, like some physical chemical simulations, like counting prime factors of really huge numbers. And to do all that, you need lots of processors, you need lots of transistors in every processors. So modern supercomputers are really huge, they consume kilowatts of energy, and yeah, why would we need to invent something different? If you might say, if this performance is not enough, then we just take a computer with 1,000 billion of transistors, not with 10 billion of transistors, and then we get the performance we need. The problem is, it's not quite like that. If only it would be. Of course, you can get more computational power by increasing an amount of transistors or increasing amount of processors, but certain mathematical problems that modern computers are trying to solve just don't scale well on the current computational model. First, there are some physical constraints, then there are some ecological constraints because of high voltage this computer needs, and then, of course, it won't solve our problem even if we build something even more performant as we have now, at least not completely. So that's the part where quantum computing kicks in. I would like to start with this simple mental experiment. It's called Schrodinger Kit. I believe some of you might have heard about it. Put your hand up in the air if somebody has. Nice. Let's take a quick recap. You have a cat that sits in the box. You have a radioactive element that is in superposition state, that is half decaying, half not. And you have a hammer that's connected to this element with some toggle. And if the element has decayed, then the hammer falls and breaks the glass with cyanide oxide and dies. But if a radioactive element doesn't decay, then the hammer doesn't fall and the cat stays alive. The funny thing is, you cannot know for sure without opening the box if the cat inside is dead or alive. So you basically need to open the box with your hands, look inside, and check, the cat is dead or not, the cat was lucky and it's alive. Another interesting thing, if the cat has died and you open the box once again, you don't get a cat zombie. The cat is alive, is dead even still. And another point of view, if the cat has stayed alive by opening the box, every second box opening will keep the cat alive as well. So what happens at the moment when you open the box for the first time, you break the wave function of the particle and you break the superposition state to a classical one. The picture you see here behind me, that is a picture of a quantum computer of today. You see there are a lot of tubes and connections, and it seems pretty scary. And what if I tell you that the only thing that does something meaningful is in here, so this little box. Everything else is being used in order to make the conditions that are needed for quantum computers to work. So in order for them to work, you need to make sure that this box opening doesn't take place at unforeseen moment. In quantum physics, you don't open the box with your hand. It may be some magnetic field, or it may be some particle in the air or something else that opens the box for you and breaks the whole logic behind it. So what the scientists have done, they have created an absolute zero temperature inside of it. It's minus 273 degrees inside of this quantum computer. That's colder than it is in outer space. And also the thing is shielded from Earth's magnetic field completely. And it is also absolute vacuum, so there are no air particles inside, not even inert ones. And inside the computer, we're not working with the transistors anymore. We're working with elementary particles, like this. Scientists call it a qubit. Depending on your computer architecture, you could use a photon, like basically you trap a particle of light inside the system and make it work, or you use some electrons or ions of the atoms. And if a classical transistor can only have two states, 0 and 1, who could tell me how many states can this particle have? Or at least in which state is this particle on this slide at this concrete moment? Somebody? Sorry? Infinite, exactly right. So basically there is no chance to know for sure what state will this particle have when you open the box. To solve this, scientists have found a way how to trigger this quantum state on and off. I'll explain that in a second. But you need to solve a problem when you have multiple qubits in one computer system. There is a phenomenon that's called quantum entanglement. You can imagine that as having a group of children, and you try to arrange them in some particular order. So you take one child, put it like this, and say, here, stand still, do something meaningful. And this time, all other children start running around wildly, screaming, waving their hands. And as soon as you reach out to get another child and to put him to stable position, the child you've been working before stands up and runs away. And you need some kind of sophisticated algorithm to make sure that all the children you need to be working at the moment are there and do something meaningful, not just run around. And I'd like to show you the simplest quantum algorithm out there. It's called Deutsch-Jürzer algorithm. It comes from the year 1992. And you see this capital H over here and here and here. This is exactly the quantum circuit that is responsible for toggling this quantum superposition state of a particle. So you have, at this point, you have two qubits, two quantum transistors, one here and one here, and you trigger their state with certain circuits. But I'm not going to bore you with this one. Let's get back to our coin problem. It's exactly the same, but on more concrete example. Let's imagine that two qubits that you have are not some abstract quantum particles, some scary things, but both qubits are coins. And the first coin you turn in such a way that you look at the obverse side. And another coin, you turn another way around and you look at the reverse side. At this moment, you don't know if the side is genuine or falsificated. What you do then, you put this coin to spins. You make them spin with infinite speed in different directions. One is spinning counterclockwise, another spinning clockwise. After that, you put these particles in the computer and make them do some computations. This thing here, you can imagine that as a function where you tell your computer to go and check the side of one coin. But the funny thing is, because this coin is rotating that fast, it basically has two sides at the same time. So this function is forced to check not only one side of the coin, but two sides simultaneously. And that's exactly how it works. Afterwards, you add the result of this function with another spinning coin. Don't ask me why, but you need to do that. And afterwards, you measure the coin from above, and only this one. You measure the coin that was turned to obverse side. And at this moment, when you measure it, you break this quantum superposition state, and you don't have obverse or reverse side anymore. You have a binary answer: is if your coin is genuine or falsificated. And another interesting thing: if you would like to measure this side of the coin, then you won't get anything meaningful. You get a random number here because of this quantum entanglement. On this example, you might imagine how complicated all this quantum computing stuff is. And that's exactly the point, the problem scientists are having right now. There are no meaningful algorithms at the moment that do something useful. So this whole thing is a proof of principle. If scientists won't manage to get it to work, then the best thing we have made so far is, for example, finding prime factors of number 15. That was a big success for company IBM. And basically, they built a quantum supercomputer with 5 qubits that had told you that 15 consists of 3 multiplied with 5. And another great invention comes from China. They have created a quantum computer that can differentiate between numbers 6 and 9 optically. But let's jump to future. And let's imagine then all these hurdles have been left behind us and quantum computer works. What is it good for? What can we manage to do with it? Well, the first thing that comes to mind is, of course, security, digital security. All the modern security algorithms are based on the assumption that there is no way to count prime factors of really huge numbers in any meaningful amount of time. So if some able mind will build a quantum computer, he could crack all the passwords out there in the digital world in a fraction of the time, in several hours maybe, or several days. But from another point of view, if some good company invents a quantum computer, then it could secure our digital data in a much better way. So there would be no possibility for any hacker to decode it, because quantum computers are extremely good at that. Or, for example, we could use quantum computers to make some complicated simulations, to make one element from another chemical element, to simulate these reactions, chemical reactions, physical reactions, on a very basic quantum level. Or you could use it to analyze big amounts of data in a very little amount of time. Or, for example, also interesting, you could use quantum computers to solve Rubik's Cube. You know this game, where you have a cube with different sides? That's something we could simulate with quantum computers as well. So the answer is, the question is quantum computer good to anything? Do we need to make our to make thoughts about it? Do we need to consider like switching from your laptops to quantum computers in near future? Yeah, I would say that the answer with anything in quantum world is both yes, no, and even maybe. Thank you.
Thank you, Boris. Questions? Yes, I see there's one on the back. Please.
Yeah.
As I remember, qubits, they are not stable as I know. They are not stable. It's very hard job to stabilize them inside the computer. And actually, I know that 99% of all working computers, they take it to resolve mistakes inside. So, as I know, they are not useful now, really useful for this computer because of that issue. I know.
If I get your question right, then no, you are not wrong. You need algorithms indeed that have some kind of error correction inside of them for make more complicated quantum computations. That's exactly the reason that the best thing you can do with quantum computer right now is to find prime factors of number 15. Like 15 is a really small number, and you need already 5 qubits to do that, and really complicated algorithm. For example, if you would like to find a prime number or prime factors of really huge number, you would probably need something even more sophisticated to do that. And scientists haven't figured out how to do that just yet. But there are huge research labs in Google, IBM, and other huge companies that do day and night exactly that kind of stuff. We're trying to get them to work.
Yes,
yes?
there's another question.
You mentioned a couple of times superposition state. What is it?
Quantum superposition state, it means this Schrodinger box, you don't know what's inside, if the cat is dead or alive, because the particle is in this state. So it is both, for example, for radiation, it's both decayed and not decayed with a given probability. So you need to open the box. At this moment, this quantum superposition state quits and breaks down to a normal one, to the one we have used in macro world. And then you have with a certain probability either 0 or 1 as an answer. So quantum superposition means basically uncertainty about in which state you have this particle, because it's spinning or doing something else that fast that's in all positions at the same time. Like electron. You can imagine that this electron spinning that fast that it's filling the whole space around an atom at the same time.
Yes, please.
So for particular computation, you need to be sure of that particular task to be performed.
Yeah, of course. And to do that, you have...
Yeah, and how would the uncertainty in the superposition help in this?
You have some logical circuits, quantum logical circuits, that are putting these elemental particles through a series of mathematical computations to minimize these error factors. And after a certain amount of time, or after certain operations on a qubit, you kind of turn this particle. You can imagine this as a vector, and you turn this vector to a certain position, and if you get it to 100% probability, you open the box and break this superposition state. So it's all about putting energy or subtracting energy to the system in order to move the vector to the position you need.
So 100% possibility is...
Yes, of course. All the algorithms that are out there are operating at 100% probability, because otherwise you couldn't do any meaningful computations with them. Yeah.
Thank you, Boris.